This work is entitled Characterizing Intent Changes in Exoskeleton-Assisted Walking Through Onboard Sensors. Robotic exoskeletons present the opportunity to restore mobility and independence following musculoskeletal injury. Existing exoskeleton control strategies provide varying levels of user intent matching and comfort. While human gait mechanics are well characterized at different walking speeds, it is unclear how gait changes are expressed when the human is interacting with an exoskeleton and its control strategy. The hypothesis in this work is that human intent can be deciphered based on the human's interactions with the exoskeleton as measured by the onboard sensors. 2 human subjects with substantial experience using the ExoGT exoskeleton by Exobionics participated in this study. One had a chronic spinal cord injury, while the other was able-bodied. Subjects donned the ExoGT and used loft-strand crutches as stability aids. To begin a trial, subjects walked naturally in the exoskeleton before being given a command to speed up, slow down, or make no change in gait. Trials continued until 3 repetitions of each command were completed for each of 2 gait assistance modes, free and adaptive. In adaptive mode, the exoskeleton employs predefined gait trajectories, providing corrective input at the joints when the user deviates from these trajectories. In free mode, the exoskeleton provides continuous support, similar to gravity compensation. In free mode, both subjects exhibited more statistically significant differences in joint kinematics than motor currents. These graphs show the effect of each intent change on the knee joint trajectories for the able-bodied subject with respect to the fraction of the gait cycle. There were also significant differences to the step duration and forward progression of the hip per stride following speed up and slow down intent changes. The no change command had no effect. In adaptive mode, most differences post-command were found in the joint motor currents, not the kinematics. These graphs show the effect of each intent change on the hip joint currents for the able-bodied subject with respect to the fraction of the gait cycle. Most statistically significant differences across all trials were found at transitions to and from stance phase. The user intent signal, therefore, is most detectable at these subsections of the gait. When the ExoGT was in free mode, the user intent was more detectable via kinematic changes than current changes because the user was more free to impose those changes on the exoskeleton. In contrast, the trajectory-based adaptive mode imposes a nominal trajectory, so the user intent was more detectable via current draw than kinematics, as the exoskeleton resisted the user's attempts to deviate from the nominal trajectory. Transitions to and from stance were most sensitive to intent changes, and the non-able-bodied subject was less able but not unable to express intent changes.